When will they have the test today? In afternoon session, huh?
Yeah. No, not afternoon session, before lunch. I'll announce. How long is it?
Sorry?
How long? 1 hour.
That according to you had given the question, you can give the timer. The Google form only, na, you are giving.
I don't know. Okay, let's get started. You can see, right? Can you hear me? Yeah. Okay. Welcome to the fifth and final day of the Dhyan course on Chain of Things. And this is a morning session. So I hope you are all doing good and looking forward to the last couple of lectures. In the just before lunch, we'll have the exam. So after my session, Professor Pal will speak, and then we'll have the exam, and then go for lunch. And come back with and have try to help see how to really design applications on blockchains. Okay, so today we are looking into the industrial Internet of Things and how blockchain plays a role in this. So we'll first talk what is industrial Internet of Things, because you have been hearing about Internet of Things in the last few sessions, and now we will look into Internet of Things applied to industrial systems. Can you please keep the door closed? Okay. A brief recap of what we have done so far. The first one was, yesterday we looked into scalability issues in blockchains, different scaling solutions, rollups, and decentralized oracles. And in today's lecture, we are talking about industrial IoT. What are the security requirements and other requirements in industrial IoT systems? And blockchain, if blockchain can help, if it can help, in what ways? Okay, so industrial Internet of Things include things that you have already seen in the IoT. So it consists of embedded system and some physical environment. So what we want to do is to have minimal human intervention and have industrial systems, or and have technologies that can enable applications for a large variety of applications. And it is also referred to as Industry 4.0. So it includes embedded system plus a physical environment, and this together forms the cyber physical systems. For Industry 4.0 refers to the fourth industrial revolution, and special emphasis is on manufacturing industries. So you would see that these are all terminologies that people have come up with, but essentially we would be looking into some of the applications which are useful in the industrial setting. Okay, so we'll talk about a different paradigm. Yes, last time we talked about edge, right? Edge. Did we talk edge? No. Okay. So think about the scenario yesterday, or not yesterday. I think Tuesday or Monday. Monday we looked into Internet of Things, right? And we were looking at what is included in Internet of Things. Can we keep the door closed because this the other event? Yeah. Okay. So on one end, we have all these devices. We have sensors, we have mobile phones, all the smaller devices. So many of them are resource constrained. Some of them are not. For example, your mobile phones are quite capable of doing some computation, and again sensors also. But still, these are not as do not have as much computational power as your servers. So you would see that if you look into this graph, you would see that these are more interactive, more responsive. But on the other end are massive cloud servers. You have lots of devices and lots of high-end devices. So these have more computing, more data storage compared to these devices. So it's like comparatively, you can see that these are massive. These are not, but you interact more with these devices, and where you typically collect some real-time data, and main thing that you do is collect real-time data, um, and have where you need more less response time, and having the capacity to interact very frequently, and then you send it to the server to do massive amount of computation. So these devices are so small that you can simply just sense and maybe do some very minimal computation, but for massive processing you have to send it to the server. So imagine it that you have all your devices with you, and you want to make sure that what is say the sensors, these are collecting all these information from say in the smart home and so on, and then you would like to make sure that these sensors are collecting enough information so that you can make some prediction about the energy usage and things like that. To do that, can simply collect the data, but whenever you're processing the data, doing the analytics, you need some heavy computation, and that can be done only on only on massive um, infrastructure, where, for example, the cloud. Have you heard of cloud before? Okay. So now this is another layer that most people, that organizations and many applications have come up with. This is called a fog layer. So these devices are so resource constrained that often you might not be able to do enough computation. So what you do is that offload the computation with these fog nodes. Now you might say, why do I need a fog node? I can simply send it to the cloud. Computing in the cloud is much more, I would say, much more expensive, because they have there are and it is bound by different service level agreements with these devices. So this becomes a cost effective and also a easy way of dealing with computation. But at the same time, the cloud essentially is a third party service. Essentially, it is not on, it could be servers not on the premise, but it could be somewhere else. So there's you can actually delegate the task and the trust to these nodes, which would reside in your boundaries. So these fog devices, they do real-time data processing, data caching, and you can offload this computation to this level, to this layer, and then when required you would use a cloud server. So this model, so typically many models are, many models would have the sensors and the cloud, but this having this fog layer essentially adds a level of efficiency and another level of trust, because not always you will be able to trust the third party service or the cloud, and then you would need something which is sitting on your premises to help process the data. Is this model clear? It's just a different model. Is this clear? Okay. So I will talk mostly about the security aspect of it. There's a lot of other aspects. So for example, the other aspects are efficiency. How we often discuss how these fog nodes can help improve the efficiency, and then we try to give some measures to estimate how efficient these fog nodes, computing on the fog nodes can be. It also, the efficiency in terms of not only the computation time but also sometimes the energy efficiency, and uh, the other thing that is, so one side of it is like computation efficiency and so on, and the other side is security. So security is important because we really need to build trust relationship with the devices, because these are devices that we possess, and we want to make sure that the data that we have, much of this is personal data. We are sure that this data is not, is used in a more responsible fashion. And think of setting in the industry where much of these data that the industrial devices, industrial sensors, and other devices are calculating, these are also um, these have to be kept within the enterprise. The only reason being that these have sensitive information that belongs to the industry, and that's what you want to have the trust relationship between the various devices, and you don't want any unauthorized access of this data or the devices. So you don't want attackers to come and get your devices or even be able to read the data that is gathered by these devices. And then you will have different type of data. It would be the data at rest or in transit. Data at rest essentially means that you have stored the data somewhere, and if you are storing it on the cloud server, then it all depends upon the cloud which has to take care of the data. In recent years, we have seen a large number of data breaches all over the world, which means that organizations should have extra protection when they store data with cloud services. Yeah, so for example, there was one Capital One hack where there was a employee within the organization who had essentially helped in order to facilitate that data breach by giving credentials. So you never know how organizations there could be different attack vectors and different ways to attack into these systems. So it's best to make sure that the data is as safely stored and processed as possible. So you could have the data at rest, or you could essentially have data in transit, and preventing tampering or by preserving the data integrity is very crucial in such scenarios. So for example, with the data that is stored in cloud, you want to preserve the confidentiality, retain control over usage of such data, and perform secure computation on encrypted data. Now, I keep saying this because, often we believe that if you really want to keep data safe in the cloud, what you have to do is that encrypt the data and keep it on the cloud, download the data, perform computation, and then return it back to the cloud. However, most people really don't understand that, or don't really know that you could also compute when your data is encrypted, and you can get all the same results even on the encrypted data. So essentially, it sounds like a kind of a fairy tale when I say that you can add two numbers, but these numbers are not known. You have the encrypted version of that, numbers, and you are still being able to compute on the encrypted numbers. Because when I encrypt, I don't know what the number is, right? It looks garbled strings, right? These were random strings. However, even with that, even with the encrypted data, you can do computations over the encrypted data. You don't have to decrypt the data, get the plain text information, and then do the computation. So this is the power that cryptography gives us, and it really helps to build systems which are really secure. And if you ask me whether these technologies are in place being used by someone, yes, massively, by all big corporations, and especially with all these big companies, Microsoft, Google, Amazon. They have large teams working on this sort of technologies to to ensure that you can still compute without disclosing the data, which is really a powerful technique. Are you getting what I'm trying to say? Yeah. Yeah. So essentially, you have to have the security, and this is called security by design. I'm not having another layer. Say, for example, I'm building the security when I'm designing the architecture. So that's the thing. I mean, building the system, the security inbuilt. I'm not adding another layer on top of it. And this is what we keep trying to do. Okay, so why do we need a secure architecture? The reason we need a secure architecture is that traditional industrial IoT architectures, they lack the following things. They lack mechanisms to preserve security and privacy of the system as a whole. So, for example, there are components within the system, those are secure, but as a whole, we have to ensure that the whole system, end to end, everything is secure. And also, data in transit. When the data, when the data is, when you add data, when you delete data, it should still be secure. It's not that, and imagine a setting, right? Say, for example, you have stored a file on the server, okay? And now you want to update the file. You want to add new things in the file. What would you do? In a traditional setting, okay, and imagine that you have the encrypted file on a disk or on the cloud. Now, in a traditional setting, what you have to do is that you have to download that data on your device. You have to make all the changes, and then you upload it back again, right? Now, what happens with this approach? The problem with this approach is that you are actually uploading, downloading, uploading. This is expensive, right? Because if you are thinking massive amounts of data, which you really don't want to keep on your disk, you don't have enough disk space. That's why you are using the cloud service. Now you are again uploading, downloading, uploading. It really does not make sense. So this kind of data where the data is dynamic, you want to add, delete, modify things, it is really helpful when we have mechanisms which can encrypt already with the new changes on the data. So this is very powerful, right? This whole idea is much more powerful because now you do not have to download all your 1 TB of data or 1 petabyte of data and add all that you need and then upload it back, right? You can do it on the fly, and that's what I call the data in transit. Similarly, you need efficient algorithms. They don't have efficient algorithm to do things in real time. Real time is very important because think of your sensors which are monitoring say the fire alarms and all. You need that real time thing. You cannot wait till the fire has destroyed the property or it has caused harm to people, right? You have to make that real time decision. And that is why latency in real time data processing is extremely important. You cannot really have a let it take its own time to process. And then we need efficient algorithms to reduce overhead on low-end devices. So if you have say low-end devices, even this the Raspberry Pi that we saw, um, that has some computing. Things of Arduino and other devices, these are much more much more resource constrained, and we want our algorithms to run on these. Now, those are real big challenges. If a server is computing all these big operations, then it's fine. But if you're doing something on your device, it's not going to be, you have to make sure that these are efficient. It's not very energy consuming. You don't want your phone to get really hot or your device to get really hot and then burn out doing some heavy computation. You really cannot. And then most of them, they would have, if they are relying on third-party cloud services, they have to ensure that there is trust. So essentially, we have an objective of decentralizing the entire traffic and bring computation to the edge, or to the fog, while ensuring security. So instead of doing everything on the server, we add another layer in between, the fog layer, where you can do the partial computation, and that will reduce, that will help, that will transfer the trust to your side. Now I'll give some examples. So this is perhaps, you have seen this sort of a thing in I think in Monday or Tuesday. You have seen all these layers, right? The perception layer, the cloud layer, the application layer. Only thing that you haven't seen is this layer, perhaps the fog layer. Have you seen? No. So this is the one where, it is something that can be added to make things a bit more efficient. And what would you do in this layer? So for example, in your industrial setting, you have a large number of IoT devices. You would have surveillance cameras, you would have smart equipment, you would have RFID tags, sensors, and so many things. What you could possibly do is take the help of this layer. When you are taking this information and doing some pre-processing in this layer before you send it to the server. What does a pre-processing help? What is the type of pre-processing that we might want to look for? So think of this particular setting. You have got sensor data, right? And instead of sending all your data, you send some aggregate information, right? So aggregate information that is being aggregated securely on this fog layer. And when you send the aggregated information to the cloud, the cloud will not be able to see what the individual sensor data is. And that essentially, because your individual sensor data can reveal a lot about, the type of work that you are doing, the behavioral pattern of the people, of the device, and also in what environment they are being deployed in a very granular fashion. So you don't want that granularity. You don't want the cloud to know about that granularity. Say, for example, you really don't want what is happening throughout the day, but you just want at the end of the day, this is what I've come up with. You really don't want to bother whether the smart meter, the smart device is monitoring throughout the day and to be able to and have data. Say, for example, it is collecting a lot of data during the morning compared to in the evening. You don't want all these sort of behavioral prediction to be made by the server, and that's it's important that you don't send all the information, but you aggregate at this layer before sending it to the server. I'll give you one other example, because this is an example that people have. There's a lot of work being done in this. And the example is that, you have all these devices, right? You have many devices, and these devices are collecting a lot of information. Now, what happens is that depending upon the information they collect, you want to figure out you want to train an AI model to being able to make some predictions in the future, right? So, for example, there has been this study, looking at how emojis work and then make a prediction of what sort of things will come up next. So in these sort of cases, you would see that the data is being collected by the devices. These are, if these are sent to the server, just like that, then the server will know exactly what is happening. Or think of a scenario where you have the medical devices, it's collecting medical data and it's trying to predict how this what is going to happen next by looking at the information that is being collected by sensors. They're trying to predict, maybe, if it is if the patient will be affected, or patient will be affected in the next 1 hour or so. So you want to build models that can predict, make those predictions. But if you send your raw data to the server, it is actually giving out a lot of sensitive information about yourself, right? Your devices are getting all this information, collecting all this information. So what you typically do is that you encrypt this information to the sorry, you collect this information and send it to the server in a way that the server is not able to get any meaningful information about the user, or it not going to get the sensitive information that is being collected by the devices that the user is using. So in all these cases, you would need to ensure that whatever data is being collected here is encrypted and sent over to the cloud. And this layer can help do that. It will also help, say for example, this layer will look into the data storage. It will make some decision making whether to send it in the cloud at all or do it on prem. These are also decisions that are being taken here, because this layer is within the organization. So it's very easy for this layer to interact with the devices and then make a decision as to whether to send it over to the server or keep it to the processing in this layer. So this fog layer essentially offloads a lot of these, helps offload a lot of computation from the cloud to this layer, and that's why it's really important that this fog layer is also a trustworthy layer. It's not that my data is corrupted and it's being um, uh, when it is in the fog layer. Okay, I'll pause here. Any questions, anyone? No questions.
Will the information be missing if you said it will be sent in an aggregated way? So will there any loss of information?
Yeah, that's a good question. So if I'm aggregating information, will there be a loss of information? What do you all think? So it depends. What am I trying to achieve? If it's like, I'm achieving, say, for example, I just want to have averages, then it's okay if I have this group, I sum the group wise instead of individual values, and then perform all the averages together. Or I could essentially group them in separate buckets, have the averages, and then find the average of everything, right? You see, no information is lost in this case, but there could be information that you want, that might be lost when you're aggregating. So that's why it's a choice to be made. Okay, but that's a good question. Any more questions? Okay. So this is so there are we'll talk about a few such challenges in the IoT space where we need techniques that can help secure the data, and then we will see how these can be used for the blockchains, or why blockchain is necessary in the first place. So the first example is that you want to aggregate data securely. And this is a classic case. I mean, the classic example of this, that you have smart meter data, and you want to aggregate all these smart meter data. So what is a smart meter? Smart meter is like your electricity meter. It collects all the information from all the devices that are running in your home or that environment, and then it tells which, in a more granular form, it just gives you how much electricity has been the electricity usage. But at a granular level, it can also say, look, because the fridge was running, this is the amount of this is what you have got, um, and then the geyser was running, so on. And you could have like more fine grained usage of electricity. And the smart meters typically can give you this more fine-grained measure. But think about it, when you are looking at this meter reading, you will see that anyone who is looking at this meter reading will be able to understand your pattern. So, for example, think about it that they are looking into the pattern that your morning, during the morning, or maybe from 8 o'clock till 4 o'clock, there's no activity. I mean, everything is like more or less shut. So you will see that every day is the same pattern, or maybe 5 days a week is the same pattern. And what it reveals, etc., is that during this time, no one is in the home, right? So an adversary who is looking into the data and making some calculated, is looking into the data, can say, okay, fine, no one is here at this time, so this might be the time when if it's a malicious intent, that can come for a burglary or something, right? So different, and when we think of such attacks, we think that these are all made up, right? Because how many times will someone look like this and be able to come and do this? But if you think a little bit more carefully, it's just a more sophisticated way of doing things. If you try to think that many people would observe, if they want to do a burglary, they will keep observing you for a long time. They just don't come and, okay, grab something and go. If they really want to do a well-planned burglary, they have to get all this information to make a targeted attempt. And this is where you don't want your grid or meter to have enough, to be able to give all this granular information, right? You don't want everything to be so granular. So in those cases, for example, you would like to have a more aggregated way of doing things. And that's the reason why, one example is that, one of the reasons why we are aggregating is that we don't want that fine-grained thing. We are good with, a more post-grade type of data, data collection or data usage. So there are a lot of these projects, especially in Europe, where people are really crazy about privacy, and the privacy laws are also very strong. And these smart meter aggregation, or aggregating securely with the smart meter, is a very important project for them, because they don't want the residents to be really giving out a lot of information about their patterns. So that's why it's important that you aggregate, but you aggregate securely. What does it mean to aggregate securely? So one thing is that all your data that you're collecting from the devices is being aggregated at a meter. But think about it, if all the data was in the clear and the smart meter is there at your in your locality. So the way things work is that there are meters in your house, then it's meter in the neighborhood, and then these are collected in that hierarchical fashion. So many homes would have they would have their own meter, and then there would be one in the locality, and then there would be one in the entire in the entire building complex. Say for example, you have these buildings. They have one here because these are the 4 buildings over here, and then it would be like, all the buildings together would be, another 4 buildings. They would have they would have a meter here, and then so on. So these are being collected from the house, and then these are being collected within that residential complex, and then you collect at a more higher level of the neighborhood or something. And you want this data. If one of these smart meters, these are aggregators, are corrupted, then all the information about the individual houses are revealed. And that's why you want to do a secure aggregation where you would like to aggregate on the encrypted data. So if this is D1, D2, D3, D4, you don't want this meter to know how it works, so you are encrypting it and sending it out. So this is a place where your secure aggregation is needed, and there are mechanisms to do secure aggregation on the encrypted data. I'm not saying how, but I'm letting you know that there exist techniques. Now, those who of you are interested, you can go and have a look into what the techniques are. But I just want to say why, the why part of it here. Okay? And what we are trying to achieve here. Does this make sense?
Yes.
Does this make sense? I don't need it. You might be thinking, why am I doing this? Right? Do you? Is it required? You're surprisingly quiet today. I think the food has done, has made you sluggish. Okay. So there are ways to deal with this. So for example, if you have these devices, you can think of this aggregation being done at the fog layer in an industrial setting, just like we are doing at a home. In the home setting, in the industrial setting, you could have like similar IoT devices, and they are, these are being, your aggregated things here. Not only. Okay, there are 2 things. So this problem essentially is a little bit different. So okay, so let me tell about that as well. So one thing is that you are encrypting the values. The other thing is more crucial. It is that this meter, the data D1, D2, D3, D4 are actual data that are being collected by these devices. Why am I saying this? Because it can be that there's a attacker who has got this device and it is injecting its own data, right? It's also possible, right? So what you need, how will you prove that it is my data? Okay, now this is from day 1. Huh? Louder.
Public key.
What public key?
By signing on the data.
Signing. By signing, yes. You have to sign. You will be doing this with the public key cryptography. That's fine, but you have to sign the data. So essentially, you are signing the data. So you are sending some signature, you are sending some signature, and so on. And this aggregator, instead of sending a lot of this, okay, so there's another scenario that we can consider. So you have all these devices, say, the sensor 1, sensor 2, sensor 3, sensor 4. So all these, if you were to say like, look, I'm having D1, sigma 1, D2, sigma 2, D3, sigma 3, D4, sigma 4. This is the data that we are sending. I'm signing the data and sending it. So whoever is verifying this at the fog node, they have to ensure that sigma 1 is the correct correct signature for the first message, so a second message, and so on. Now, if you have granular data, and you are sending, say, for example, for every minute you are sending, or every second you are sending the sensor reading, every time you are verifying, it is a lot of data and a lot of signatures. So for every time you are verifying. It's a lot of computation essentially you are doing just to verify. Instead, what you can do is that you can aggregate the signatures. So you would have data D1, D2, D3, and D4. These will be your data, but you have an aggregate signature which will aggregate all the signatures, sigma 1, sigma 2, sigma 3, and sigma 4, so that you have to verify only once. You're not verifying hundreds of signatures, but you are verifying one signature. It adds efficiency, right? Yes or no?
Yes, ma'am.
Yeah. So these things are very useful in an industrial or any setting, be it a home setting, residential area setting, or an industrial setting. These are techniques that can be used to optimize the computational overheads. And honestly, I'll tell you, if you're thinking traditionally, this will never come to our mind that we can do it. And that's what I want you to take back, that beyond what we are seeing, there can be tools in my toolkit that I can use to make things more efficient. And how come here the toolkit is like a cryptographic toolkit, but it could be like other toolkits and for other domains. So essentially, your toolkit should have a set of tools which can optimize your efforts. And in order to build that toolkit, you have to really understand how things are working, why am I doing this, and how these toolkits, how the tools work. So be it blockchain, be it cryptography, be it AI, be it whatever, having built, understanding this underlying toolkit is very important. So if there's something that you would like to take back, is like, how do I build this toolkit? So that I have a toolkit. Now I know if this application comes, this is what the tool I use. This is important. Else, if you don't have a knowledge of this toolkit, for everything that comes, you are really searching for it. And then once the problem is done, that's done. But if you have already built a toolkit, then given anything, I know I can use my toolkits appropriately. You understand? I'm talking philosophy now, not blockchain or anything. This is a philosophy. Building more on your toolkits or understanding how the tools are used will really help. So this is, for example, a good tool how you aggregate signatures, because it comes in various forms. Even in blockchains, a good example, since we are talking about this, let me talk about blockchain protocols, how it is used. You remember we talked about the consensus in Ethereum? What I said was that the validators were giving their attestations, were attesting. Did I say that? The validators were attesting to the block. Did I say? What does attesting mean? I'm signing. I have my signature on it. I have attested it. And how would the nodes verify that these are correct as attestations? They would verify because they would verify the signatures, right? They would verify the attestations. Now, you could use the same technique there to aggregate these attestations together and verify only once. You see? Same technique. That is also same technique. Think of these, instead of D1, D2, D3, D4, it is like same D1 being signed by different people, different nodes. Same D1 being signed by different nodes. So they have signatures, but you're now aggregating aggregating all these signatures together. It's a little bit different here. It is the same S1, but you are signing it, by different people are signing it. So it's the same S1, but there are different nodes who are signing it. So you would have S1 sigma 1, but the same S1 being signed by sigma by say A, B. So they are also signing S1 sigma 2 and so on, but now you're aggregating again the signatures. It's similar technique. So that is a toolkit now I have. Now I can do it for this, I can do it for something else.
Can I compare this to encryption? Like
This is not encryption, this is a signature. This was what I was talking about, encryption. Okay. Now I'm talking of signatures. Yeah.
the password we get a star. So can I relate this to that, or it's not related?
Password.
The username and password we type.
Yeah.
It will come like in stars.
Yeah.
Whatever we type, it comes
Yeah.
in stars.
And what is it? What is the? How are you mapping it to this problem?
You said the S1, so everybody is signing the same, but the value inside is different. So that's why I'm asking.
Not really. So what was the thing? What was the analogy? So you're signing and then the stars are coming, then what happens?
No, we don't see the value inside.
Oh. No, that is that you just don't want to reveal the value. So it's just a usability thing. Like you still have that, you're still putting that thing, but it's not visually seen. So this has nothing to do with this one.
So which means here the values are also same.
Which value? Yeah, so this S1, S2 are all same. Here the S1s are different and there are different, it comes from different sources. Here S1 is the same, but everyone signs it. So that is an attestation that was there in that problem. So this is another problem. This is another problem. But what I'm trying to say, the signature aggregation can be done. Okay, once more. This is a block. Say this is a block. Same block. Now this is being signed by, A, B, and C. What they will do, they will add this. This is S1. Or A. Okay. Now, so you have to verify this separately, right? Instead of that, what you can do, you can merge all the signatures. You can merge all the signatures. You have to verify only once. How you are merging, that there are techniques. But that this can be done is something to take back.
So we are merging because everything is done by S1.
We are merging because we don't want to validate, we don't want to verify each and everything. If there are 100 nodes which are attesting it, we have to verify 100 attestations.
So like in train, they just check one Aadhaar card for a team.
Yeah, something of the sort. But it's a little bit different in that, you are trusting all others which are there with this particular person. It's a little bit different here because here is like this signature is derived from all these signatures. It's somehow combination of all these signatures. In your Aadhaar and in your group verification that you were talking about, you trust one person. That's why you are saying that others are also right. That's not the model here. The model over here is that all these persons, they are together. If you had a group Aadhaar, that's the thing. For example, everyone has Aadhaar in the team. Now you have a group Aadhaar. See, then only once, validation only once. Yes.
How are you going to retrieve the data if you want to see the question data? Because
this is a different question. The data is always there. S1 is always there. This is a signature. Signature, with the signature, you have the data and the signature. Data and the signature. There's no encryption. No encryption.
how it is going to aggregate, like adding one by one? Like
Yeah,
A,
so
B, C?
aggregation, I'm not talking of that. There's a little bit of maths behind that. So this anyone who is interested can look up this particular thing called BLS signature, Bonnet-Lynch-Shakam signature. These are very good for aggregation and very useful. I mean, in various things, it's used for so many things, including blockchains. Okay. Yeah. Yeah. So if you want to put this thing in the industrial setting where you would have all this, then this is what you do. You would have packets, you would have signatures, you can aggregate them together so that the verification becomes very easy. Okay. A small pause. Does this make sense? Does this make sense? Does this make sense? Why I'm doing it? Why? Not how. I'm not shown how. Make sense? No. Okay. Okay, we can take it later then. Okay. It makes sense to anyone? Okay, that's fine. Yeah, so okay, but let's move because I'll talk about a bit, this particular thing, and then we'll talk about the blockchain setting. Yeah. So this is another scenario that typically comes in. So this is just like you had a secure aggregation. You want to share your data. So you have a sender who is sending, who is encrypting the data, and there's a, it is stored on some server, and then there are different clients who want to decrypt the data. Okay, so it's stored in the server in an encrypted fashion, and it can be used by clients when they want. They can decrypt it and use it. So so the first thing is that you have a sender, and the sender has some kind of a, some keys with it. So it generates the ciphertext, the encrypted ciphertext, and then it stores the ciphertext in the server. And later, if someone wants to get, so one of the ways is that you don't want the server over here to know what the data is. So if there were two parties, say this is the sender and this is the receiver, then what would you do? You would have the server. What will you do? Can anyone tell me what will I do to protect the data, say D1 or M? If you have M, to protect the data, what will I do? Encrypt. Encrypt. How I will encrypt? By using encryption algorithms. What are the keys that I will use? Public key? With whom? Whose public key will I use? Huh? Sender's public key. Anyone has a different answer? Receiver's public key. Yeah, so you will send it to the receiver's public key. So you encrypt with receiver's public key and send it across to the receiver. So this is your C. So you send the C, you store the C here. The server does not know the public key, so the secret key of the receiver, so it's not able to decrypt, right? But the receiver knows a secret key of itself, receiver, so it can easily decrypt, right? So this is a technique that you can also use in an, if you have a industrial kind of a setting where you have the cloud server essentially does not know anything, but you store the data that can be retrieved by someone else. There are only two parties. This is what you can do. But things can get a little bit more complicated, in which there could be many receivers. So there are receivers like R1, R2, and so on. So there has to be some other mechanisms to do this. So just at this time, because I'm losing you, and in terms of, these are concepts that might not be, that we might essentially skip at this time. What I wanted to let you know that you could also encrypt your data in a way that any receiver, R1, R2, R3, this will no longer be R1. I can encrypt in a way that any of these receivers can decrypt, who are authorized to decrypt can decrypt. But if they're not authorized, they will not be able to decrypt. So in this case, you would need a particular key over here that will enable these receivers to decrypt. R1 can decrypt, R2 can decrypt, R3 can decrypt, but if R6 is not in the authorized list, it cannot decrypt. But what I'm trying to say here is that these techniques are so powerful that you can also selectively decrypt. Users can selectively decrypt, and there are mechanisms to do this very efficiently. Okay, makes sense. Okay. So again, forget about what is written on the slide. This is not what is written in the slide. This slide does something else, but I really want to, at least this, you guys understand this part or no? Huh? No? Okay, what is the problem? Do you understand that the sender might want to send some message or store something that many people might want to decrypt?
In the slide you have.
No, forget the slide is not the same what I'm said.
Okay.
Forget about the slide. Forget about the slides. The slide does something else. This is just a, I've just made something else. It is not the same. But this is a very simpler scenario than what is on the slide. A simpler scenario, does this make sense that there could be one sender, but the same, instead of only Bob, I can have Bob, Charlie, and many people trying to decrypt the same message, right?
Yes,
But there are ways to do that. Just saying it here. And these are helpful in a industrial, in any IoT setting, because you want to collect all these data from these devices, and there could be many processing centers whom you want to target it to. So it could be, I'm collecting the same sensor reading for for this for user 1, user 2, user 3, user 4, or to be used with some device, or the device which is processing it, or sending it to multiple receivers. So for example, I have one message and I would like to send it to multiple receivers. There are ways to do that. So this is not what's on the slide. Maybe I should talk about this. Okay, so okay, maybe I should talk about this first and then this. maybe I'll just talk about this because this or this. No. Okay, maybe I will say I will talk about a simpler scenario. So I can't tell this before I tell this. Okay. Okay, so maybe I'll okay, so let's talk about this because this I think you can relate to. Okay. Okay. Let me see. I'll just disconnect for a minute. I'll just get back on this. Okay. Into this. Okay, so did not get that figure that I was looking for. So let us consider this scenario where you have a sender and you have a receiver. That's here. So as I said, now you don't have just one receiver. You have multiple receivers, and you want to make sure that all your receivers or the clients are able to decrypt the message. So one way of doing this is as follows. You have stored your ciphertext on the server. However, it is different users would need different keys to decrypt it, right? If I have encrypted with C1's key, then only C1 can decrypt, but not the others, right? So one way of doing it is to use a mechanism which actually helps to re-encrypt the keys in a way that any client can decrypt it, given that it has permission. So what I do in this case is that I take the message, I convert it into a ciphertext, and we'll see what ciphertext. When I'm saying a ciphertext, how do I construct the ciphertext? So I encrypt with the ciphertext of an intermediate, the fork node. Instead of sending this, the C prime is the fork node's private, public key. And what I want to make sure is that this, in the step one, the fork node's public key is used to encrypt the data, and this is sent and stored on the cloud server. Okay. Now, because it's stored with the fork node's public key, the server cannot decrypt any of this information, right? Now, what I do is that every time a client requests to get that the data, what I'll do, I'll forward this request to fork node, and the fork node will encrypt it in a way that can be accessible to the client. So one naive way of doing it is that the fork node over here can decrypt it and then re-encrypt with the client public key to just give it to the client. So in a naive way, what you can possibly do is that at the, because the fork node is on my end, in my area, I can trust this fork node. If I can trust this fork node, then a useful way of doing it is that it will send it to the fork node. The fork node decrypts it and then forwards it with the client's public key. And every time a client comes in, you can encrypt it with that particular client's public key and send it across. So this is a way I can use if I trust the fork, right? If I trust the fork, then this is a way I can essentially do it. However, if I don't trust the fork, then what do I do? If I trust the fork, I send it to with the fork's public key. The fork can decrypt. Every time a new user comes, the fork re-encrypts it with the user's public key and sends it across, right? So this is one mechanism to do if I trust the fork public key. I trust the fork. But it could also be that I might not trust the fork, right? And in this case, how will I do it? So in this case, I have a sender, but I have multiple receivers. And I have a message M. What I will do, I will encrypt it in a way that can be, this encryption key will be such that the ciphertext C, everyone gets a ciphertext, but it can decrypt with its own plain text, own private. Okay, so I am deriving a key over here based upon the secret key of SK1, SK2, SK3, and so on. I'm not going to say how in this case, but this is essentially a classic case which is called which essentially takes a message and then encrypts in a way that can be decrypted by all the receiver nodes. So there's also a mechanism, and this essentially was a very common mechanism when you had pay-per-view the TV. So what it means is that, for the channels you have paid, you will, the TV means broadcasting, right? You're broadcasting the same content everywhere. Why are we doing this? Okay, first of all, why are we doing this way? Why are we not sending them different messages to different users? The only reason is that for the same message, we have to send different ciphertext to different people, right? In this approach that we talked about previously, I would essentially send a public key. I would send a message, different message here, different message here, different message here, and so on. But in that case, I can send just one message or pass the message in a way that only if you have the public key of R1, if you have the secret key of R1, you will be able to decrypt. If you have the secret key of R2, you will be able to decrypt, but no one outside the group is able to. So this is also a powerful technique that is that are used in these sort of settings to make it very efficient. So because we want efficient methods of encryption, and also you don't want the bandwidth to be very high. So you don't want your ciphertext to be very, very large, or you send multiple ciphertexts. The ciphertext sizes are not small. Okay, so let's move now and see why are we using blockchain in the first place. So if you remember correctly, if I have two parties, I talked about the book, example of a book, and then example of a server. So I'm going back to that, and I'm asking this question: what if whom do I trust? And what if my parties are not, not honest? So we saw three examples. We saw when the client is honest. We saw when the case where the client honest and server dishonest, and then we saw both were dishonest. So we tried to figure out what we took the help of the blockchain. And in this case as well, we will take the help of a blockchain if one of these parties are not behaving correctly. So think of this scenario where you have the IoT device, you have the fog node, and you have the cloud, all separate entities. What does this IoT device do? It is sensing some information, it is sending to the fog, and the fog essentially stores it in the cloud. Okay? And if there's a client who wants to retrieve this information, what it will do, it will ask the cloud to send this information, so send the file, which is encrypted file, and then it will verify whether the file is correct or not. It will accept or reject, right? Depending upon if the file is correct or wrong, correct or not. So one way of doing it is that you have just, here there's only one receiver, just, it's not a multiple receiver setting, it's just only one client. So what will they do? They will take all this, the encrypted the data. It will take all the data, and it will have some kind of a shared key. I will come to this concept of shared key. First let us discuss the problem, and then I will say what is, how each of these parties can behave maliciously. So at this place, you have the IoT device and the fog node. You want the cloud to store an encrypted version of the data because you don't want the cloud to know what your data is. So this is where you don't want the cloud to know, but where you have to retrieve the client, retrieve the data. The client has to retrieve the data. So what can I do? Now, what can go wrong? The cloud can give a false data to the client, right? The cloud can change the data and it can give it to the client, because even cloud, it can generate some spurious data, right? Instead of M, it will encrypt with the public key of the client and then send it to the client. So that might not be the case. I mean, that's not what we want. So in this case, the cloud can be a dishonest entity. And what we can do, even the cloud can be a dishonest entity. Even the client could be dishonest. It might say, look, I did not get the right content. When it tries to decrypt, it might say that I did not get the right content. And in this case, it has to somehow rely on the blockchain, because again, you have parties who are not behaving honestly. You have only one honest party, which is the IoT device, but and the fog, and then you have these cloud and the cloud and the client, which is not behaving honestly, and therefore you rely on the blockchain again to ensure that everything works properly. So this is another use case where, in a normal setting, if everyone was honest, there is no need for blockchain at all. But because there are dishonest parties, you want to make sure that everything is well taken care of. So what you could possibly do in such a scenario is that very simple. What you could do is that in such a case, whatever file you have stored here, so you have the file that has been given here. Now you encrypt the file f prime, store it on the cloud, and with this key, and later share this key with the client. Now this file, which is encrypted with this public with this key that the fog has shared with the client, you can decrypt it with that key, and the client can read this information. So somehow you have to make sure that the client is able to retrieve the file F that has been sent by the IoT device, or this the original device. So in this case, one naive way to do is that initially you say that the fog has sent the right data by again writing, just like yesterday. What we will do, we will say that, okay, I'm committing to the data, and this is the data I'm encrypting. And later, when I share the key with the third party, with the client, I can say that, yeah, this is the data that has been encrypted, because I can read from the file, I can read from the blockchain that this data was committed to. So one thing, the cloud cannot change the content of data, because at the start, the fog had written, kept the digest of it on the blockchain. So now, when the client retrieves it, it matches with whatever data it has seen. And if it is not matching with the hash digest of the data that was essentially stored on the cloud, then it says no. I mean, this is not the data. So we are using, there's more to it that I'm not telling, but at the crux of it is that if the cloud is injecting spurious information, then you can definitely figure out, because originally the fog had written something on the chain, the digest on the chain, so that it knows that this is the data that I was supposed to get. So it does not know. The file is not written on the blockchain, but only a digest is kept. But when the client retrieves it, it knows, it checks with the digest to figure out that it was the same data. So again, coming back to the previous case, that when you have client server, which are where you have malicious parties, you rely on the blockchain, and this is where you can use this blockchain. Okay.
How they are sharing the keys?
Yeah. So in this case, it would be like very simple. So one thing could be yeah, you have something. Okay, anyone has a solution? How are they sharing keys? Anyone? Okay. So there could be multiple ways. One thing is that it could be the fog is selecting a key. Okay, fog is selecting the key, encrypting it with that key, and later at some stage it is giving the key to the client, and the client can decrypt using that. Okay, so in order to do that, what the client does, so I said that this figure has more to it, so maybe we can go through that. We can go through that. So you have the fog. So this is, say, the fog, and this is the client. This is the client, and this is the cloud. You have the data M. Initially, you can this fog can select K, and this is your blockchain. So you can keep the hash of the message here at the start, encrypt it with K, send it to the cloud, right? And at the start, it actually gives the money. The client pays the money. So what happens is that, okay, the cloud also, so because the cloud is essentially the storage device, it has to store the data correctly. So this is, say, your ciphertext. Okay, maybe I'll just say C is your ciphertext. So the cloud essentially sends the ciphertext here to the client. Now, what happens is that if once it has paid the money using an off-chain mechanism, you can send the key K to the client. The client can decrypt and get the message. So it will decrypt using the key K, check it with the get the message M and check with the hash. Say M primed, check if M primed is equal to HM. If yes, then it knows. So even if the cloud is cheating here, does not matter. So the cloud can cheat, it can have its own key, it can, generate some spurious message C prime. But don't worry, nothing happens. Once the client receives C prime, it gets some message M double prime, but it essentially sees over here that it is not matching, and then it can say, yes, I have a problem. Yeah.
And
But
they might
because
share the key using TCP layer,
Yeah.
they are sharing the keys.
Yeah, it's off chain. Yeah.
Is there any hacking may happen from sharing the key?
There could be, like, say, for example, if the channel is corrupted, then it's a problem.
It's again come the security issue, ma'am. It's a secured key, so you are using the secured layer over TCP.
Yeah.
And using different security methods, I think. So different security algorithms. So it's fully secured.
Okay.
So you can think of this. This has a little bit more to it, but I've simplified the problem here. This picture is a little bit more, but let's not talk about that. Let's keep this problem simple, have this following assumption to make things easier to see why the blockchain is used. Okay, so this is one way where you have data sharing on blockchains. But what I did not talk about is that that in the industrial IoT setting, one thing which is very important is also that of the tracking. Because in the tracking scenario, every time your data is moving from one place to the other, you can record it, you can timestamp it, and so that you know what is the movement, what happens as the data flows in the whole system. So one example of just say yeah, so one example that I want to mention over here, and I'll stop with this. So think of this particular model. So these are all IoT devices. They're collecting a lot of data, and they are training models on these IoT devices. And what they're doing is that once these models are trained on this data, they're sending it to the server. The server aggregate the model parameters, and then it sends back the model parameters here. And then they have got the set of model parameters. The devices are training more data using this model parameters. sending it to the server. Server is aggregating the model parameters, sending it. So essentially what you want to do is that my device is collecting some information. I want to build some machine learning model. Your device is also running some data. You want to create a machine learning model, and everyone's. But we want to make sure that the final model that is created essentially depicts everyone's inputs. However, what we could have done is that we could have all sent our data to the server, and server takes all our data from all our devices and then runs the ML algorithm there on the server, and then gives us back the result. However, why we are not doing it? If we send our data to the server, then it's a big problem, right? We are essentially disclosing our data, and that is not what we want. That's why we are doing things in small silos on our device. We are having such small data, we are generating the parameters, and then we are letting the server aggregate it, and then distribute the parameters again, and then we train again, and then we continue till we converge. So this is a good model because think of a scenario where there is a lot of hospital data at one hospital, and then the hospitals, they themselves don't want to share the data amongst themselves, but they want to make sure what is the cause of a disease, and they want to collect all this information from patients in first hospital and the second hospital and the third hospital or the fourth hospital. But in none of these cases they want to share the data with one another. So one of the way is that the server itself takes all the data and runs it. But in that case, a server who is running will know all the information of all the hospital patients of all the hospitals that are involved. But this is not what we want to do. And that's why, we are using this kind of a model. And this is a very useful model to have. It is known in literature as federated learning model. Many of you, might have seen this or read about this. One thing that does not happen here is that there's no mechanism that tells me whether the server is correctly aggregating all this information. What the server can possibly do, it can inject some spurious things and manipulate the model, right? It is possible. In this case, there's no way to handle this. So what am I going to do? There has to be a mechanism to show that whatever I'm getting from each of these devices is consistent with whatever aggregation is happening on the server, right? Is this problem clear? Like, what am I trying to do? You are collecting device, you are collecting data, you are collecting data, you are collecting data. You are not sharing amongst yourself because it's like your personal data or the data that you have collected. So now the server can generate spurious things and make a biased decision by coming up with outputs which are not consistent with what was collected, right? So to think that you are predicting some disease and you have collected data from 3, 4 hospitals or 100 hospitals in the country, but because the server who is operating it has some vested interest, so they are manipulating the data and doing something else. That's not what is what is required. So what would I do? I'll leave you with this problem, and I want you to think after your exam how you would solve it. And then we can come and discuss in the second half. Okay? Okay. So I'll stop here. Thank you. Yeah. Sorry, 11 o'clock.
So guys, I'm writing you the feedback form. Please fill it.